August 19, 1942, Dieppe, France. In 6 hours, roughly 6,000 men, predominantly Canadian, will attempt what Allied High Command calls a reconnaissance in force, what history will call something else entirely. The plan is, on paper, elegant. Storm the port, hold it, extract intelligence, withdraw. The reality, 3,623 casualties before noon. A full third of the raiding force dead, wounded, or captured. Tanks drowned in the surf. Landing craft raked by enfilading fire from clifftop positions the aerial reconnaissance had failed to mark. Dieppe was not merely a military disaster, it was a data point. And the engineers and planners who survived it, and those who studied it from London, drew a conclusion that would reshape the entire strategic architecture of the war in the West. The conclusion was this: you cannot take a port, and not intact, not against a prepared defense. The Atlantic Wall was not simply a line of guns and concrete emplacements. It was a logistical system, a blockade, engineered in reverse. The Germans had understood something fundamental. A modern army does not die from bullets alone. It dies from the absence of fuel, ammunition, and food. And the fastest way to starve an invading army is to ensure that every deep-water port along the coast of France is either too heavily defended to capture or too comprehensively demolished to use. Both options suited the Wehrmacht perfectly. You storm the port, you lose thousands of men on the quay walls and the jetty approaches in kill zones pre-registered to the centimeter. By some miracle, you breach the defenses, the garrison engineers detonate the lock gates, collapse the harbor cranes, demine the approach channels, and scuttle block ships in the deepest berths. Either way, the port is gone. And without the port, your army, however large, however brave, begins to starve within days. Let us talk about numbers, because this war, more than any before it, was a war of arithmetic. Operation Overlord, as planned for June 1944, called for the landing of 156,000 men in the first 24 hours across 5 beaches on the Normandy coast. That figure is well known. What is less discussed, what the popular histories tend to gloss over in favor of the human drama of the beaches, is what those 156,000 men required simply to remain combat effective. 26,000 tons per day, every day. That is the figure that dominated every logistics conference in the 18 months preceding D-Day. 26,000 tons of ammunition, rations, vehicle fuel, medical supplies, replacement parts, artillery shells, and engineering materiel per day, for a force that, by the end of the first week, was expected to number not 156,000 but closer to 300,000, and which would continue to grow division by division until the breakout. To put that tonnage in physical terms, 26,000 tons, loaded into standard 2.5-ton military trucks, requires over 10,000 vehicle movements per day, simply to shift supplies from the waterline to the forward dumps. And that calculation assumes a functioning port. The Normandy coast offered none. Cherbourg, the only deep-water port of any consequence within the invasion zone, sat at the tip of the Cotentin Peninsula, heavily garrisoned, its approaches mined, and its facilities pre-wired for demolition. Intelligence assessments, later vindicated in every particular, indicated that Cherbourg would be rendered operationally useless within hours of any German withdrawal. The port was not captured until June 26th, 3 weeks after D-Day. It did not return to anything approaching full capacity until late August. By that point, the Allied armies had been ashore for nearly 3 months. 3 months during which every gallon of fuel, every artillery shell, every medical dressing had to come across an open beach. a beach exposed to the full violence of the English Channel, a beach subject to tidal ranges of up to 20 feet, a beach that offered no natural shelter from the prevailing southwesterly swells. The men who planned Overlord understood with cold clarity what this meant. Without a solution to the port problem, a structural engineered solution, not an improvisation, the invasion of Western Europe was not a military gamble. It was a logistical suicide mission. The army would land. It would fight. And then, somewhere between D+30 and D+60, it would begin to run out of everything, and it would stop. The seed of the solution was planted, characteristically, by Winston Churchill. In May 1942, Churchill drafted a memo to Lord Mountbatten, then Chief of Combined Operations. The memo is terse. It runs to less than 100 words. "Piers for use on beaches," he wrote. "They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Don't argue the matter. The difficulties will argue for themselves." That final sentence, "the difficulties will argue for themselves," is perhaps the most precise summary of the engineering philosophy that would produce the Mulberry Harbors. You do not waste time cataloging the problems. You design around them. What followed was one of the largest and most secretive construction programs in British industrial history. The engineers of the War Office and the Admiralty were presented with the following specification: design, build, and deploy, in absolute secrecy, 2 complete artificial harbors. Each harbor must be capable of handling the throughput of a medium-sized commercial port. Each must be operational within 14 days of D-Day. Each must be able to withstand channel weather. And each must be transportable across open water, floated across the English Channel, in pieces. The solution arrived at was not a single structure, but a system of interlocking components, each solving a discrete part of the problem, each dependent on the others. At the outermost perimeter, the bombarding floating breakwaters, cruciform steel structures, 60 feet long, designed to absorb wave energy through hydrodynamic drag and reduce the sea state within the harbor basin to workable levels. Inside the bombardons, the gooseberry block ships, aging merchantmen and obsolete warships, sailed to position and deliberately scuttled in a curving line to form the inner breakwater. Concrete was poured into their holds in the weeks before the crossing, not for structural integrity, but to ensure that when the seacocks were opened, and they sank cleanly without drift to pre-surveyed positions, displacement physics applied with the precision of a surgeon, and at the heart of the system, the Phoenix caissons. The Phoenix was the critical element, the component on which everything else depended. Each Phoenix was, in engineering terms, a hollow, reinforced concrete hull. But that description fails to capture the sheer physical scale of what was built. The largest Phoenix units were 204 feet long, 56 feet wide, and 60 feet tall. They displaced, when floated empty, approximately 6,000 tons of water. They weighed, in dead weight, approximately 2,000 tons. They were, in effect, concrete ships. Each Phoenix was built with a series of internal compartments, separated by reinforced bulkheads. Embedded in the base of each unit were scuttling valves, seacocks, mechanically actuated, which, when opened in a precise sequence, would flood the ballast compartments in a controlled cascade. The unit would then settle under hydrostatic pressure onto the seabed at a predetermined rate. Too fast, and the structure would impact the bottom with sufficient force to crack the hull. Too slow, and tidal currents could swing the unit off its bearing before it grounded. The engineering tolerance was, by the standards of wartime construction, extraordinarily fine. The concrete mix, a high Portland cement formulation with a low water-to-cement ratio, had to achieve sufficient tensile strength to resist the scouring action of tidal currents once sunk, and sufficient compressive strength to bear the lateral pressure of water at operational depth without spalling. And test specimens were broken in hydraulic presses. Mix ratios were adjusted by fractions. Pour schedules were calibrated to the ambient temperature of the construction sites. Those sites were everywhere and nowhere. Across the Thames estuary, the River Clyde, the dockyards of Southampton, Portland, and the Solent, in gravel pits turned into temporary dry docks, in requisitioned shipyards where the workforce had been sworn to secrecy. 212 Phoenix caissons were under construction simultaneously. The workforce numbered in the tens of thousands. Shift patterns ran around the clock. Concrete was poured in winter temperatures that required heated formwork and curing blankets to prevent frost damage. The workers knew they were building something large, something heavy, something that floated and then was meant to sink. And they did not know where it was going. They did not know when. And in the spring of 1944, as the Phoenix units were towed, one by one, to their holding anchorages off the south coast of England, where they were kept in water shallow enough to be refloated if damaged, deep enough to be hidden from casual aerial observation, the clock was running. D-Day was weeks away. Across the channel, the Atlantic Wall waited. And somewhere in the logistics files of Supreme Headquarters, Allied Expeditionary Force, the number sat unchanged, immovable, absolute. 26,000 tons per day, June 6, 1944. While the histories fixed their gaze on the beaches, on the ramps dropping, the men falling, the tide running red at the waterline, something else was happening 12 miles offshore, something slower. And something that made almost no noise in the historical record, and without which the entire operation would have collapsed within the month. 160 tugboats. That is the figure. 160 tugs, fleet ocean tugs, harbor tugs, salvage tugs commandeered from merchant operators along the British coast, straining against their tow lines in the pre-dawn darkness of the channel, hauling the component parts of 2 artificial harbors toward the coast of Normandy. The aggregate tonnage under tow on that single night exceeded 2 million tons. Concrete, steel, pontoon sections, floating roadway segments, pier heads, and the 212 Phoenix caissons, each one a 6,000-ton concrete hull riding 4 feet above the waterline, presenting a windage profile roughly equivalent to a 4-story building. Speed of advance, 4 knots. Maximum safe towing speed for the largest Phoenix units, 4.5 knots. Above that figure, the hydrodynamic drag on the flat-bottomed hulls exceeded the structural capacity of the tow fittings. The towing brackets, cast steel lugs embedded in the caisson walls during construction, had been tested to a load of 150 tons. The calculation allowed no margin for error. If a tow fitting failed mid-channel, a drifting 6,000-ton concrete hull in a mine-swept lane was not merely a logistical problem, it was a navigation hazard of catastrophic proportions. The route across the channel had been swept of German mines, theoretically, but a swept lane in 1944 was not a guaranteed lane. It was a lane in which the probability of a mine encounter had been reduced to an acceptable statistical threshold. Then that threshold had been set by men who would not themselves be making the crossing at 4 knots in an open tug. The tow formations were staggered to minimize interference between units. Each caisson required a minimum separation of 300 yards from its nearest neighbor to allow for shearing in cross-tidal currents. The navigational coordination required to move 212 units, 160 tugs, and the associated fleet of escort and attendance vessels across a 60-mile crossing in darkness, in radio silence, through a body of water simultaneously being used for the largest naval bombardment in history, was by any measure an achievement of operational logistics that has never been adequately celebrated. It was not glamorous work. The men on the tow bridges were not soldiers. They were merchant seamen and Royal Navy ratings, watching their compass bearings and their tow-line tensions, listening to the diesel exhausts and trying not to think about what was beneath the water. The first Phoenix units arrived off the Normandy coast on June 7th. Positioning was conducted by survey teams using pre-plotted coordinates referenced to fixed shore bearings. Each unit was brought to its designated position, held in place by attending tugs, and then, on the signal of the positioning officer, the scuttling valves were opened. Hydrostatic pressure equalized through the ballast compartments. The freeboard dropped. The hull descended, and 6,000 tons of reinforced concrete settled onto the seafloor of the Bay of the Seine, becoming in that moment the foundation wall of an artificial port, 212 times. A breakwater creates shelter. A shelter is necessary, but not sufficient. To move 26,000 tons of supplies per day from ship to shore, you need a road. And a road, in the context of a tidal beach with a 20-foot range, presents an engineering problem that has no precedent in conventional civil construction. The answer was the whale roadway system. Each whale roadway consisted of a series of steel pontoon sections connected by articulated pin joints that allowed adjacent sections to flex relative to one another as the tidal level rose and fell. The roadway did not fight the tide. It rode it. The transition between the two states, the periodic grounding and refloating of a structure carrying heavily laden military vehicles, imposed cyclic torsional stress on every joint in the system. And each pin joint was designed to accommodate an angular deflection of up to 12 degrees. Beyond that figure, the joint would lock and the road would fracture. 12 degrees, in a 20-foot tidal range, across a roadway that extended in some configurations to over a mile in length. The geometry was unforgiving. The seaward terminus of each whale roadway connected to a pierhead, a floating steel platform large enough to accommodate a dockside crane and a queue of waiting trucks. The solution to keep it stable was the Spud pier. Each Spud pier was fitted with 4 vertical steel legs, the Spuds, which could be raised or lowered independently by rack and pinion mechanisms driven by electric motors. When the tide rose, the operators lowered the legs until they re-established contact with the seabed. Us then continued lowering until the legs were bearing sufficient weight to lift the pierhead platform clear of the water surface. The platform was now standing on its legs, independent of the tide. When the tide turned, the operators reversed the sequence. In 1944, in the middle of a war, this was robotics. It worked. The storm arrived on June 19th. Meteorological records classify it as a force 6 to force 8 northeasterly, sustained over approximately 4 days. By the actuarial standards of channel weather, it was a 1 in 40-year event. The Americans lost their harbor, Mulberry A, because it was sited on sand. Under 4 days of storm-driven current, the sand scoured. The caissons shifted. The alignment of the harbor mouth changed. The tidal flow accelerated as the geometry tightened. The Americans lost their harbor to sand. At the British harbor at Arromanches, Mulberry B survived. The reason is geological. The seafloor beneath Mulberry B is limestone. The Phoenix caissons were resting on rock. Their foundations were fixed. A site survey decision, made months before the invasion, proved to be the margin between function and ruin. Mulberry B remained operational until late 1944. In that time, it processed 2.5 million men, 500,000 vehicles, and 4 million tons of stores. The whale roadways carried convoys of 3-ton trucks, nose to tail, around the clock. The Spud piers walked up and down with every tidal cycle day after day, absorbing the fatigue loadings with a structural reliability that exceeded specification. Some elements of Mulberry B remained in place for years after the war ended. At the concrete that was poured in the Thames mud in the winter of 1943 is still in the water. The Mulberry Harbors were not a miracle. Miracles are unrepeatable. They cannot be planned. The Mulberry Harbors were something more durable. They were the product of a bureaucratic decision to solve a problem that had no historical precedent by applying industrial capacity at a scale the enemy had not anticipated and could not match. The Atlantic Wall was concrete and steel and guns. The Mulberry Harbors were also concrete and steel. The difference was throughput. The math worked. The Army did not starve. That is all.